record. 3, 2, 1. Here we go. Okay, so today we're gonna come and take a look at our example number 8, and we have the problem like you had last week. That is, we now have the load right here that is not perpendicular to the member. So we need to do something with them, and we have two of them here and here, that the load is not perpendicular to the member. So this is simple enough, you know, because I have mentioned a few minutes earlier before the class that in your exam you need to do a proper calculation for me. So I remember that Napat used to ask me maybe last time that do we need to show proper calculation in our work. I used to say no, you don't need to, but you know, I was thinking about how I approached the problem or how I do the hand calculation myself. But because of the fact that we will have the online exam, so I would suggest that you show the proper calculation as much as you can. In fact, you should always show it. Okay, so my apologies for the previous answer. Okay, so for here, let's say if you're going to do proper calculation, you should always begin with calculation of your reaction, right? Right here, you know that you're going to have this and you are going to have that. And even though, you know, the frame might look a little bit crazy, but you should know that if you look at the whole picture, you see that there is no force on the horizontal direction. So you can say that this better be 0, right? There is no horizontal reaction at all, even though this frame will be pushed to the side by the fact that they have inclined members. Okay, so we can always start off by doing that. And if you can recall that the fact that we have the determinate structure, the shape really doesn't matter. So you can do your sigma moment equal to 0 or sigma Fy equal to 0, or you can say by inspection. You should know that your reaction should be equal, right? Because if the shape doesn't matter, I can simply say that this is what we're dealing with, right? So it's simple enough. It's like a simple beam. And the total load here is 24 kilogram force. So we can easily see that our reaction is going to be 12,000, I'm sorry, and 12,000 here. But again, it would be nice if you could write the proper calculation, or if not, you should state that by inspection, you know that reaction is equal, just like that, because of the nature of the structure. So we can easily proceed to look at our member. So again, say right here, show calculation. And or statement. Okay, and if you get this correct, that's your level 1, 20%. Okay, the next step, we will go and try to complete our free body diagram. Okay, so let's go to the first piece. Now I have this. Okay, I have the force here, which I already know from my calculation of the reaction, that is going to be 12,000. So, and I also have the external load, which is a uniform load in this case. This is 2,400 kilogram per meter. Now, ladies and gentlemen, always keep in mind that you can use this load to complete your free body diagram, but you cannot use this load, which is not perpendicular to your member, to calculate your shear force or bending moment diagram. Okay, so you can say, how should I do it? Okay, sigma F y equal to 0. Okay, so you have 2400 multiplied by the entire length of this, which is 6, and then say minus your reaction, but your reaction is larger, right? And then say this better be the downward force, right? Or upward. This better be upward, right? Plus the call it VB, okay, equal to 0. So now you know your VB is going to be equal to 2400 kilogram force. Okay, that you can do, and then you can take sigma. Sorry for my sigma. I'm just, at the end of my iPad, so the handwriting is a little bit not beautiful. Let's do it again. Sigma MB equal to 0. Okay. You can also take moment at A. This is up to you. Okay. And now I know that my MB is going to be equal to my reaction 12,000 multiplied by that distance 6, right? Minus the moment due to the uniform load, which is 24,006 square over 2. Okay, but now I know that my moment is equal to 2800 kilogram meter, and the direction is, of course, to counter the moment caused by the reaction. So be very careful, because if you can concentrate very well, it will be your very own benefit. If some of you who tend to say get carried away very easily, I would suggest that you try to use different color, or just write down VB equal to 2400 here, and moment is equal to 2880 kilogram meter. Someone would just swap the numbers. Okay, so what would be the next step? Okay, the next clever step would be maybe to work your way from the right. Okay, so now we also know that we have the reaction here. Okay, and we have the uniform load acting down like this. That is also 2400 kilogram per meter. And you can use your sigma. It's a little bit, say, too close. So let me try to move to the next page, okay? There's no reason to squeeze this. Cut. Okay. Paste. All right. So we can work our way with the free body diagram in this page. Okay. Right now I have this, so I can use sigma. Oops. Sigma Fy equal to 0. Now you should realize one thing, because this member is only 2 meters long. The total force here is 4800, right? So you see, now you have to believe in your free body diagram, because when you use your sigma Fy equal to 0, you know that your reaction is larger than the total force on this member. So you should know that, you know, in the end, your V here is going to be downward. Okay. So we have 12,000 minus 4800 minus VC, right, equal to 0. So you now your VC is 7200 kilogram force, but it's downward. Okay. Any question? Oh, we have a question from the chat room. Okay, why do we have different sign for VB, and you mean this one? Okay. Why do we have different sign for VB and that one? No, we don't. VB and okay. Yeah, maybe I should clear this up, right? I'm pretty bad at that. Maybe it should be minus, okay? Better. Because if it's the same sign, it should come out differently, okay? That'd be better. Okay, thank you for that. All right, so let's come back here. Now take sigma moment. You may notice that this is kind of too easy for me. So I'm really not well equipped to write everything. I'm trying to write everything to show you. So sometimes I do some stupid human error like that, because I already see the answer. I'm trying to write the calculation process for you. So, okay. Now we take the moment at C, okay, equal to 0. So we have 1200 multiplied by 2. And then we are minus 2400, 2 square over 2. Okay. And then minus MC equal to 0. So MC is going to be equal to, what do we have here? 19200 kilogram meter. Okay. So because this term is greater than the second term, that means this moment is in this direction. Okay, so that's 19200 kilogram meter. Okay, I need to be away for 1 second, so I'll come back in a minute. Okay, I'm back. Yeah, okay. So where were we? Okay. Now, up to this point, we have completed the free body diagrams for two members, okay? I perhaps should write, this is member CD, and this is member AB. Perhaps I also should write that this is member A, B, C, and D. So the jackpot is with member BC. By now, you should be able to guess that, in fact, you don't have to do anything. You have the n forces at B from member AB, and you have the n forces at C from member CD. If they come and join force and turn out to be equilibrium, that means your member BC is complete. But on the other hand, this is what you guys should pray, right? They should come in together and provide equilibrium for your member BC, right? If that's the case, you guys are done. So from member AB, we have upward 2400 and then moment counterclockwise. So we are going to have the clockwise moment here, 28800, and downward reaction of 2400. Okay, this is from member AB, and from member CD, let me change the color a little bit so that you guys can realize that we have 22 down, so you have 2200 up. You have clockwise moment, so this becomes counterclockwise of 19200. Okay, and what's the total load here? That's 2 meters. So the total load here is 4800, right? I suppose. So it looks like that and that equals that. So, okay, let's try to complete our sigma Fy equal to 0 equation. So it's going to be pretty clumsy a little bit. 2400 plus 2400 multiplied by 2, let's say uniform load, then minus 7200, that's 0. Okay, and then you should take sigma moment. Now it doesn't matter. Maybe sigma MC equal to 0 is better. So now we have 28800, that is clockwise, okay, minus the counterclockwise moment. Don't forget the moment, minus 2400 multiplied by 2 minus 2400 multiplied by 2 over 2. We're taking the moment at C, okay? That's a summation of all the moment, and this is 0. Once we have that, we have the complete free body diagram. So this is getting a little bit more difficult to get, but I can say now that the complete free body diagram, no, this is not yet. Hang on. To have the complete free body diagram for this, I should say your uniform load here should be turned into the load perpendicular to the member as well. So the total load here is, oops. The total load here is 2400 multiplied by 6. So that is 14400. Okay. We need to turn this load into the one perpendicular to the member. So we come and take a look at our trigonometry. You know, I kind of like the 3, 4, 5 triangle very much. So that's 6. That is 4.5. That would be 7.5. Okay, it's a 3, 4, 5 triangle. And if that's going to be my angle, my cosine is 4/5 or 0.8. And my sine is 3/5 or 0.6. Okay. And if that's going to be my angle, that again is going to be my angle, right? So we need to use the cosine to turn this load into the one perpendicular to our member, all right? And therefore, I can say the uniform load prime, okay, will be equal to the total force. Let's say if I'm going to be thorough with my calculation, 2400 multiplied by 6, that's a total load, and then this is the total load, okay? Total load, which is 1440 kilogram force, okay? I'm running out of space. Kilogram force multiplied by cosine, which is 0.8. So now that becomes the total load that is perpendicular to the member. Okay, that's a symbol for perpendicular. Okay, and now we turn this back into the uniform load again by dividing this by the length of the member, which is 7.5. So you can say maybe it's a different color. Member true length. Okay, so that would be equal to, in the end, 1536 kilogram per meter. Okay, so let's say from this we can now have this. And if you really want to be complete, which you should be, there is also the uniform axial load acting on this, okay? And you just change the cosine term to the sine term, you get that. And now you have this, say, force. This is, of course, if that's the angle, that's 90 degrees, okay? So that's the angle. So that is another cosine term. This is 12,000 multiplied by 0.8. That is 9,600 kilogram force, okay? And another one, you're doing the same. That is 2,400 multiplied by 0.8, and then that is going to be 1920 kilogram. the moment doesn't need the rotation of the axis. It's going to be the same. And that is moment 28800 kilogram meter. Okay. And you should also have this component. That is 12,000 multiplied by 0.6. Okay. I don't have the number with me. No, I'm going to be cheeky. That's 1536. Okay. And if you can include that, you know, I have to say, honestly, because we are dealing with, say, moment predominantly. So if you cannot complete the axial uniform load, I would not be very, very cruel to you, but you should know how to do it and should always complete it. Okay, and don't forget that you should have this as well. Okay, that's going to be this direction. Okay, so that is the true complete free body diagram of your member. Is there any question? And you know, the second one is the repetition of the more of the same thing. For member BC, it's already perpendicular, so we don't have much to do. For I'm running out of space again. So let's say CD revisit. Okay, because in the end, what you need is this one. Be careful because it appears that I give the same angle. Okay, and you need this. It's another 3, 4, 5 triangle. Let me move upward a little bit. Okay, we have that. So you know now that let's work our way with the trigonometry first. Okay. The what did I write? I want to be in good order. I didn't write anything. So okay, let's say we have this 1.5 that is 2 meters. So that's a 345 triangle. That's 2.5. That's our angle. And again, cosine is 0.8. Okay. Sine is 0.6. And you have the total load from that is 4,800. So your uniform load here, you know, if you are going to be very thorough and very precise, you should call this omega double prime, because it may be different from the omega prime that we calculated for member AB. So this is going to be the total load again, that is 2,400 multiplied by the length 2 meters. That's a total load in the vertical, right? That we had before from this picture, 4,800. Okay, it's a total load. And then we multiply that by the theta. Let me try to use the same color. So go back, okay? All right. So 0.8. Okay. So this is the entire term is total perpendicular load. Okay. And then we divide this by the length of the member, which is 2.5 meters. Okay, so we get the number equal to, actually it's the same because the angle is the same. Okay, and for this, let's say this is of course coming from that. If that's your angle, this is going to be your angle. So this one is going to be 12,000 multiplied by 0.8, which is, you know, the same, 9,600 kilogram force. And then that is, you know, in the similar fashion. Oh, I'm sorry, I shouldn't write that. Hang on. We need this, right? So in fact, this should be the blue one. Let me try to change that so that you don't get confused. Okay. That's 12,000 also multiplied by 0.6, which is 9,600. If you go back to member CD, that's a downward force. So this should be the downward as well. That's going to be equal to 7,200 multiplied by, oh, sorry, this is 0.8, right? Yeah, okay. Ooh. That's better. 0.8, and that's 0.8, okay. So that is 5,760, and this uniform load double prime is equal to that, same. So now we have the complete free body diagram, and don't forget the moment, which remains the same, 19200. Okay. All right, so that's our complete free body diagram. So to go ahead and complete the shear force and bending moment diagram should not be so difficult now, I hope. Okay, we have 10 minutes before the break, so chances are we should be able to complete that. Okay, so now for AB. Okay, I'm going to write it in the normal way. So many of you ask if we can draw the diagrams in this direction. Of course, you can do it in any direction you wish. 9,600 and 1,920. This is, excuse me. Okay, 1,536 kilogram per meter, and then the moment 2,880. Okay, so shear force diagram is going to be simple enough. I have made the point before that you are in third year now. You are more than halfway through becoming a professional engineer. Should we always turn it back for a free body diagram after count? Well, it doesn't matter as long as you're comfortable writing. Okay, you can carry on your work with this picture, but I run out of space. You can draw your diagram down here if you want. You know, the shear force diagram, negative, and like that. You know, or you can do it over here. But I run out of space, and I want to make it clear, so I start anew. But it's entirely up to you. Okay. So if I flip it this way, I have 9,600 going upward as a positive value. And I know that this shear force will bring my shear force diagram down to right here, minus 1920. Okay. So again, let me remind you that the sign on the shear force diagram serves to show you the direction of the shear. Because if you look at the sign convention for the plus shear, this is plus shear, left up, right down. Okay, so when you have the value on the right minus, it means this is your sign convention. It's down and up. You see, minus sign on the right, it's up. So you know this is the upward shear. Okay, you guys should master the sign convention since statics. If you have not, I suggest this is the high time that you do it. Okay. So let's go. Okay, this is the shear force diagram. And the bending moment diagram, we begin from the hinge. So the moment is 0. That is your positive area. So your bending moment diagram is going to look like this. And that is this, right? It's counterclockwise on the right, which is the sign of positive moment. So that means this is a negative area. It will bring this down a little bit, but it remains positive. Okay. So yeah, because I say you should show your calculation, so I better do the same thing. First of all, it's the distance where you're going to have shear equal to 0, and therefore you have your maximum moment, right? So that means this, let's say it's okay, it's equal to 9600 divided by 1536, which is 6.25 meters. And by that, you can show that you got your Mmax equal to, you can calculate the area of the shear force diagram, of course, a half of 9600 multiplied by 6.25. Okay, and that is 30,000 kilogram meter. Okay, and your you can also show that your MB, but you don't have to if you don't want to. This is for your own check, because we've got from our free body diagram that it is equal to that. But if you're curious, you can also try to calculate and see if it comes out to be the same. So that's the value of the Mmax minus the rest of the area, which is 1920, and true length is 7.5 minus 6.25, right? Same. Or you can just, you know, it's a repetition of what you have done with your free body diagram. But that's one down. Okay. For member B, C, what you have is that one. You have, remember that the shear will not be the same because we are now using the forces perpendicular to the member. 1920 is perpendicular to AB, but 1920 is not perpendicular to your BC. So this one is 2400 down and 7200 up. You know, writing the uniform load like this is a bad habit of me. I don't suggest you do it because, you know, you can have the upward uniform load. But for the sake of, you know, going quickly, okay, and we have the moment on both ends now, 28800, and that is 19200 bad habit. You should always have the unit. Okay. So that's that. So the shear force diagram is pretty simple. It's down on the left, so it's minus. And it keeps going down with this. Meet the upward on the right. Upward on the right is a negative, right? So that's negative 2400 and 7200. You know, if it's very obvious like this from the free body diagram, because you have completed the free body diagram, you may not have to write the calculation. Okay. And then the this bending moment diagram on the left is the clockwise, so it's positive. That is 28800, and then because of the negative shear, it should go down and meet with this. Again, on the right is counterclockwise, which is a positive sign convention. So that's that. Okay, that's a shear force diagram. Unit is kilogram force. This is bending moment diagram. The unit is kilogram meter. Okay, it's a BMD. And you should write your value here as well, 30,000 and then 28800. Okay. So that's A, B, and B, C. So let me try very quickly to complete CD as well. Okay. I hope you don't mind. You also have that. Downward of 5760. We have upward 9600. We have this 1536 kilogram per meter, and we also have the moment here 19200 kilogram meter. Okay, so pretty much the same thing. Shear on the left, that's negative because it's downward. It's minus 5760. The unit formula will bring it further down until it meets up with this upward shear on the right, which is again the negative sign, minus 9600. Okay, so with that, we can go on and try to meet with this. This is again clockwise on the left, so it's positive moment. Okay, this is shear force diagram, kilogram force. That's 19200. Okay, and this is negative shear. You can prove that, but you probably have done so in your free body diagram, that the bending moment at D is 0 by say 19200 minus the total area, that's a half of the average value of 5760 plus 9600, and then that's the average height, right? That's the average height, and then multiply by this distance, which is the length of the member. I think it's 2.5 meters. Okay, so that should be 0. And your bending moment diagram should, oops, sorry, the slip of the iPad come down to be 0. So that is the end of everything. Okay, so you see, because of the nature of the structure, we have the frame and we push everything down. So chances are it's going to be, everything is going to bend like a typical simple beam. So you have the positive moment throughout the system. Okay, and one thing that you should notice is that a member like this in the system, like member BC, there's always moment in that. Okay, you cannot have a simple beam in the system anymore unless you put the internal hinges on B and C, and then you will have a simple beam, but that will cause your structure to be unstable as well. One thing I like to point out, I got the question from one of your friends. That is, if your free body diagram is correct, everything will fall into places. If your free body diagram is not correct from the first place, chances are your shear force and bending moment diagram is going to be messed up as well. So if you have the proper free body diagram, it should lead you to proper shear force and bending moment diagrams. And I always emphasize on the fact that you get your free body diagram correct first. It is fundamental to everything you do in civil engineering. It shows that you have the balance of force. It shows that you have the balance of your system. And if your system is properly balanced, you have equilibrium and everything should fall into places for you. Now, this is applicable in every level. What you have now is what we call a simple equilibrium in the elastic world. Your world can easily turn into the inelastic world in the future. But regardless of the system you're in, no matter how advanced it is, elastic, inelastic, first order, second order, you will hear these terms in the future. It is always under equilibrium. And equilibrium comes from free body diagram. It doesn't matter which system you are in, elastic or inelastic, first order, second order, they always have free body diagram. Okay? And it doesn't matter whether you study structure, soil mechanics, or water structure, they always draw free body diagram. Okay? So any question, folks?
Can you scroll down a little bit?
Okay.
In AB member.
Okay. I got a question in the chat, so could you please wait one moment? It's a question says, which one is more universal, kilogram force meter or kilogram meter? You know what? Because I write kilogram force, right? And then for a moment, I drop the F out because I feel a little bit awkward. So, and you notice that. So, I actually, to write, normal people would write the kilogram force just kilogram. There's no F in it. But I try to add it a little bit from time to time to remind you that this is the kilogram force we are talking about. You should not confuse the kilogram as a mass. It is a mass or mass, mass in the US or mass in British. It is generally a kilogram is the unit for mass. So when we use it universally, especially in this country, I would like to remind you from time to time that we are talking about the kilogram force unit, not kilogram as a mass. But so to write for the moment, I suppose dropping an F is not entirely wrong, because if you ask me, I have never seen anyone write the KGF and then M. Okay, so please go ahead with the question. What's the question again, please? I'll scroll down, right? Sorry. There. Okay. So you just want to see the bottom part of the page?
The bottom part.
Okay, the MB?
AB. Scroll a little bit.
And this is the bottom of the page, dear.
In
the next
Zoom,
page, maybe?
You cannot see it because the last one is have the toolbar.
Toolbar. So can I move it like this? Can you see it now?
just
Yeah.
just scroll down.
I can't scroll down anymore, dear. Just I'm at the end of it.
Okay. Stop. Okay.
So I have to press my finger here.
Okay ค่ะ thank you ค่ะ
So that's done.
done ค่ะ
Okay. All right. So I'm gonna stop the record now.